Hello dear students, the next topic in functional analysis is orthogonality. To define orthogonality, we will consider one set. So let u1, u2 so on up to un be the subset. This is the subset of Hilbert space H. We are in Hilbert space, so I am considering one set which is the subset of your Hilbert space H, okay, such that here each element of this subset, say ui, is not equal to 0. We are defining orthogonality. For that we are considering one set which is subset of Hilbert space H. Each element of this set is not equal to 0. Then the set ui, collection of ui, is said to be orthogonal, if, when the set is said to be orthogonal, if the vectors are pairwise orthogonal. That means I will write it mathematically. That is, if inner product of ui comma uj is equal to 0 for I is not equal to j. So if I and j are not equal means it is a pairwise orthogonal. The inner product of ui comma uj is not equal to 0. Then you can call this set as orthogonal set. Now the set ui is said to be orthonormal set, if inner product of ui comma uj takes two values. I will denote this as delta ij. We have seen this delta ij even in our continuum mechanics. So it has two values, 1 as well as 0. Inner product of ui comma uj takes the value 1 when I is equal to j, and it takes the value 0 when I is not equal to j. So the set ui is said to be orthonormal set if inner product of ui comma uj is equal to 1 when I is equal to j, and inner product of ui comma uj is equal to 0 when I is not equal to j. This is the definition of orthogonal set as well as orthonormal set. Now let's prove one theorem. The name of the theorem is Pythagorean theorem. Statement goes like this: if f is orthogonal to g, then norm f plus g square is equal to norm f square plus norm g square. Here you can observe they have given f is orthogonal to g. That means inner product of f comma g is equal to 0. We have one result, that is orthogonal set is symmetric. That means inner product of f comma g is equal to 0, which is equal to inner product of g comma f. This is symmetric, okay. So I will use this as my data and I will prove that norm f plus g whole square is equal to norm f square plus norm g square. So first, how I can write norm f plus g whole square? I can write this as inner product of f plus g comma f plus g. So this I can split this in this way, f comma f plus g plus inner product of g comma f plus g. Again you can split this step, that is inner product of f comma f plus inner product of f comma g plus inner product of g comma f plus inner product of g comma g. From given data, f is orthogonal to g, so inner product of f comma g is 0 and inner product of g comma f is 0. So what we will get? Inner product of f comma f plus inner product of g comma g. We know that inner product of f comma f is nothing but norm f square plus this is norm g square. So initially we have considered norm f plus g whole square and we are getting norm f square plus norm g square. This is what we are supposed to prove, right? So this is nothing but your Pythagorean theorem. We have a problem. So this is my first problem. Let V of R of a Hilbert space of polynomials. Here we are considering the polynomials with inner product defined by, they have defined the inner product in this way, that is inner product of f comma g is equal to integral over 0 to 1 f of t g of t dt. Okay, this is the way they define the inner product and they have given the value of f of x as well as g of x. We have to find out inner product of f comma g and norm g. So how we can do this? Since we have f and g are functions of t, I have to convert my function in terms of t. So this is f of x. So what is f of t? F of t is t square plus t minus 4. What is g of t? It is just that in the place of x we are replacing x by t, that's it. This is t minus 1. So first I have to find out inner product of f comma g. Inner product of f comma g is equal to integral over 0 to 1 f of t means t square plus t minus 4 and g of t is t minus 1 into dt. So multiply these terms and integrate with respect to t, then apply limits from 0 to 1. So if you integrate this, you will get t power 4 by 4 minus 5 into t square by 2 plus 4t within the limits 0 to 1. Apply the limits. First I will apply upper limit 1 over 4 minus 5 by 2 plus 4. If you apply lower limit, you will get 0. So if you simplify this, you will get the value 7 by 4. Okay. So now this is my inner product of f comma g. Next I have to find out norm g. So to find out norm g, we know that norm g square is nothing but inner product of g comma g. So find out what is inner product of g comma g, then take square root of that, you will get norm g. Okay. So inner product of g comma g is equal to integral over 0 to 1 g of t into g of t into dt. We have g of t is t minus 1. Substitute the value 0 to 1 t minus 1 into t minus 1 into dt. This is integral over 0 to 1 t minus 1 whole square into dt. If you integrate this, you will get t minus 1 whole cube divided by 3 within the limits 0 to 1. So if you substitute the values, you will get 1 over 3, I will take it outside. So if you apply upper limit, it is 0 minus lower limit is minus 1. So it is 1 over 3. So inner product of g comma g is 1 by 3. Then this implies norm g is 1 by square root of 3. So this is norm g. The next, let's move to the next problem. If B is a complex Banach space whose norm obeys parallelogram law, so we have already seen what is parallelogram law, and if inner product is defined by this, okay, that is 4 into inner product of x comma y is equal to norm x plus y whole square minus norm x minus y whole square plus I into norm x plus iy whole square minus I into norm x minus iy whole square. This is, you know, polarization identity, right? If inner product obeys polarization identity, then we have to prove that B is a Hilbert space. So B obeys parallelogram law means, what is the statement of the parallelogram law? Let x comma y belongs to Hilbert space H, then norm x plus y whole square plus norm x minus y whole square is equal to 2 into norm x square plus norm y square. This is my parallelogram law, right? So since we are in complex Banach space, I will consider elements in B. Let x comma y comma z belongs to B be some arbitrary, and I will consider one scalar, say alpha. Alpha is scalar. Okay, so this is my parallelogram law. I will call this as equality 1. So consider polarization identity, since they have given that your inner product is defined in this way, which is nothing but your polarization identity. So take down that 4 into inner product of x comma y is equal to norm x plus y whole square plus norm x minus y whole square minus I into norm x plus iy whole square, x minus, right, plus I into norm x plus iy whole square. This is minus. I will call this as equality 2. So now we have to use both the inequalities and we should prove B is Hilbert space. That means we have to prove inner product of x comma x is equal to norm x square. Second condition is inner product of x comma y whole conjugate is equal to inner product of y comma x. Third property is inner product of x plus y comma z is equal to inner product of x comma z plus inner product of y comma z. And the fourth property is inner product of alpha x comma y is equal to alpha into inner product of x comma y. We have to prove these 4 properties in order to say that B is a Hilbert space. Okay. So here, combining this 3 and 4th property, we can write inner product of alpha x plus beta y comma z is equal to alpha into inner product of x comma z plus beta into inner product of y comma z, which is similar to your linearity property. Okay. So now let's consider one by one. I will prove first property now. So to prove first property, since our norm is defined here, I have inner product of x comma x. Here I have inner product of x comma y. So you have to replace y by x, right, in order to get inner product of x comma x. So put y is equal to x in equality 2. So what you will get, 4 into inner product of x comma x is equal to norm x plus x whole square minus norm x minus x whole square plus I into norm x plus ix whole square minus I into norm x minus ix whole square, right? So this is 0 and this is 0. So you will get 4 into inner product of x comma x is equal to norm 2x square plus I into norm x plus, in this term I have taken x common, so you will get x into 1 plus I norm whole square minus I into Here again take x common, you will get x into 1 minus I whole square. So now I will use the property, that is norm AU is equal to mod A into norm U, where A is a scalar. So using this property, you can write this as 4 into inner product of x comma x is equal to norm 2x square plus I into mod 1 plus I whole square into norm x square minus I into mod 1 minus I whole square into norm x square. If you find out norm of this, you will get, if you take modulus of this, we have mod 1 plus I. Using the concept of your complex analysis, you can write, if you have a plus ib, you will write it as square root of a square plus b square, right? So this is how I have written this. So you will get root 2 even for 1 minus I. Okay, just substitute these values here. You will get 4 into inner product of x comma x is equal to norm 2x square plus I into, this is mod 1 plus I is root 2. So if you take square, you will get 2 into norm x square minus 2 into I into norm x square. This 2 gets cancelled. So you will get 4 into inner product of x comma x is equal to 4 into norm x square. 4 gets cancelled. So you will get inner product of x comma x is equal to norm x square. So the first property holds good. Now let's move to second one. To prove the second property, what I will do is I will take conjugate on both sides of my equation 2. Okay, so if you take conjugate, here you will get a real number itself. If you take norm of any number, it's a real number. So I have written as it is. Okay, now replace x and y, that means interchanging x and y in your equation 2. Here you have to interchange x and y. So if you interchange, what you will get? Four into inner product of y comma x is equal to norm y plus x whole square minus norm y minus x whole square minus I into norm y minus ix whole square plus I into norm y plus ix whole square. What we supposed to prove? We have to show that these two are equal. For that I have considered this, right? So we have to find out what is I into norm y minus ix square and I into norm y plus ix square. Okay, so to find out that y plus ix whole square, you can write this as norm into, I will take I outside, I as common. So I will get x minus I into y. Because I into I is I square value is minus 1, minus into minus it is plus. So you will get the same thing. Okay. Now since I is scalar, take it outside, you will get modulus of I into norm x minus iy whole square. Similarly, you can find out norm y minus ix whole square. Here I will take minus I as common. You will get x plus iy whole square. Okay. So again modulus of minus I whole square into norm x plus iy whole square. So norm x plus iy whole square means you will get x minus y. Sorry, you will get, this will become 1. So this will become norm x plus iy whole square. Now we have to find out what is norm y minus x whole square. So norm y minus x whole square is equal to, I can write this as minus 1 into x minus y whole square. So again this is nothing but minus 1 whole square into norm x minus y whole square. So you will get norm x minus y whole square. So substitute these values here. You will get 4 into inner product of y comma x is equal to norm x plus y whole square minus norm x minus y whole square plus I into norm x minus iy whole square minus I into norm x plus I y whole square. If you take conjugate on both sides of your equation 2, your imaginary terms sign gets changed. This is minus, this is plus. Okay. So now compare, I will call this as equation number 3. Compare your equation number 3 with this equation. I will call this as equation number 4. So if you compare those two, you can write 4 into inner product of x comma y whole conjugate is equal to 4 into inner product of y comma x, which implies inner product of x comma y whole bar is equal to inner product of y comma x. So this is your property 2. Now let's prove property 3. To prove property 3, instead of xyz, I will consider u, v, w. So what I have to prove, inner product of u plus v comma w is equal to inner product of u comma w plus inner product of v comma w. This is what I have to prove, right? So by equality 2, I have 4 into inner product of u comma w is equal to norm of u plus w whole square minus norm of u plus u minus w whole square plus I into norm u plus iw whole square minus I into norm u minus iw whole square. This is from equality 2. So again you can write inner product of v comma w, that is 4 into v comma w is equal to norm v plus w whole square minus norm v minus w whole square plus I into norm v plus iw whole square minus I into norm v minus iw whole square. We have these two using polarization identity or your equation 2. So now I will call this as equation number 5. This is my equation number 6. What I have to do, I have to sum these two, right? Our final answer should be adding these two. So now I will add these two equations. So from this you can write 4 into inner product of u comma w plus inner product of v comma w is equal to norm u plus w whole square plus norm v plus w whole square. This is one term. Take minus outside, you will get norm u minus w whole square plus norm v plus w whole square plus, if you take imaginary I outside, you will get norm u plus iw whole square plus norm v plus iw whole square. Again if you take minus I outside, you will get norm u minus iw whole square plus norm v plus iw whole square. So from these two equations we got one single equation. I will call this as equation number 7. Okay. So now using 2, you can write 4 into inner product of u plus v comma w. This is u comma w, this is v comma w. I need my LHS part also. So again equation, by using equation 2, I will find out what is u plus v comma w. So this will be equal to norm, first term is u plus v plus w whole square minus norm u plus v minus w whole square plus I into norm u plus v plus iw whole square minus I into norm u plus v minus iw whole square. I will call this as equation number 8. At last what we supposed to prove? We should show that equation 7 and 8 are equal. For that, let's do some of the simplification process. Okay. So now using equation 1, that is from our parallelogram law. Using parallelogram law, what we have? Norm u plus v plus w whole square is equal to norm u plus w plus v whole square. You can write this as 2 times of norm u plus w whole square plus norm v whole square minus norm u plus w minus v whole square. So if you want to compare, you can compare these things what we have in parallelogram law. We have norm x plus y whole square plus norm x minus y whole square is equal to 2 times of norm x square plus norm y square, right? So this is x plus y whole square, this is norm x square, this is norm y square, minus this plus shifts to minus, so it will become minus norm x is u plus w, y is v. So this is how we used parallelogram law here. Okay. Now you can group this term as norm u plus v plus w whole square is equal to 2 times of norm u plus w whole square plus norm v whole square minus norm u plus w minus v. I am just grouping these terms. Okay, whole square. So again from parallelogram law you can write 2 into norm u plus w whole square plus norm v square. Substitute here now. You will get minus 2 times of norm u square plus 2 into norm w minus v whole square minus norm u minus w minus v whole square. In first step what we have done, here we have applied our parallelogram law. So we got these two terms. So in this step we are applying parallelogram law to this step. Before that what we have done, we have just grouped our terms. Okay. So I have just multiplied this negative sign overall and I have taken 2 outside. So 2 into norm u plus w whole square plus norm v square, minus into plus it is minus, so minus norm u square, minus into plus it is minus, so this is norm w minus v whole square, minus into minus it is plus, so norm u minus into minus plus v minus w whole square. Now you can shift this term to your LHS part. So you will get norm u plus v plus w whole square minus norm u plus v minus w whole square. This term has shifted to LHS part, remaining thing as it is. I will call this as equation number 9. Now interchange u and v in your equation number 9. Interchange u and v. Okay, so if you interchange, you will get v plus norm v plus u plus w whole square minus norm v plus u minus w whole square is equal to 2 into norm v plus w whole square plus norm u square minus norm v square minus norm w minus u whole square. Call this as equation number 10. Now add equation 9 and 10 and divide the whole equation by 2. You are adding equation 9 and 10 and you are dividing whole equation, the resulting equation, by 2. Okay. So what you will get? You will get norm u plus v plus w whole square minus norm u plus v minus w whole square is equal to norm u plus w whole square plus norm v plus w whole square. Norm v square gets cancelled, norm u square gets cancelled, minus norm w minus v whole square minus norm w minus u whole square. After cancelling all the terms, you will get the final resultant in this way. Okay, I will call this as equation number 11. Now replace, wherever you have w, replace w by I into w and multiply I on both sides. Okay, so what your equation 11 become? We have to multiply I on both side of our equation. So I into norm u plus v, here I have w, I will replace it by iw whole square minus I into norm u plus v minus iw whole square is equal to norm u plus iw whole square plus norm v plus iw whole square minus iw minus v whole square minus norm iw minus u whole square. So now, but we know that norm iw minus v is equal to norm v minus iw. Just take I outside. In previous step we have did right in this way. If you solve in this way, you will get norm iw minus v as norm v minus iw. So substitute this, you will get I into norm u plus v plus iw whole square minus I into norm u plus v minus iw whole square is equal to, oh I have forgot to multiply I. So I into this term, I into norm u plus iw whole square plus norm v plus iw whole square minus norm